Yeah, g'day, it's Charlie ZL2CTM. I've been meaning to do a video like this for a while now. Over the past several radios, for the small signal amplifiers, the IF amplifiers, the RF antenna amplifiers, say the microphone amplifier, the preamplifier leading into the audio circuit, and the preamplifier leading into the power amplifier, I've taken quite often, well, they're nearly virtually always been a common emitter amplifier, but the way in which I've done the biasing has been subtly different each time. And I wanted to do this video to try and get some feedback coming from you guys and girls, or a bit of a discussion going on, what is the best way of doing it. So what I wanted to present here was my understanding of the best way, well, a way or the way or whatever, to do a common emitter amplifier. Now, when I went to school, if we would look at biasing, say, this amplifier here, we would use the characteristic curves for the particular transistor of choice. I find it very, very hard to find these characteristic curves online for the transistors that I use. This supposedly is the characteristic curves for the 2N3904, which is a common little transistor I've been using several times. But even so, here it's IC here, or the collector current, versus VCE, the collector to emitter voltage, for various values of the base current. And I note here this base current isn't actually labelled, so my suspicion is it's 10, 20, 30, 40, 50 microamps. But anyway, back at school we would set the value of VCE, which would be at full cutoff. So VCE would actually rise up to our VCC value. Then over here for IC max on the vertical axis, or the y-axis, it would be at full saturation, so VCE equals 0. What current, our maximum current, which would be VCC divided by RL plus RE. And once you had those two values, for example, say 13.8 and let's say arbitrary 10 milliamps, you would draw a line, and then you would look for a point to bias the transistor that effectively gave you the maximum amount of swing to give class A biasing. But I guess where I have difficulty, and where I've been trying to get, what I've been forced to get away from this approach, is you just don't get or can find these characteristic curves. In this particular case here, you would find a value on that DC load line that gave you the maximum amount of swing before you got a cut off here. So we want to always have the VCE above, and a rule of thumb there is 1 volt. So once you've found that quiescent point, which would be right, say there, you would find the nearest beta current. So if this was, for example, 10, 20, 30 microamps, then that would be it. Once you've got your 30 microamps, you can then start working out the various values. But I guess my question, and why I want to open up this particular email for some, or this video for some feedback, is in the absence of characteristic curves, if you just have in your little hand a 2N3904, what's the best approach for designing what I prefer, a common emitter voltage divider biasing amplifier around that small signal? So I guess that's what it is. There's no given RL, and in fact RL in some cases for an RF amplifier may be an RFC, a radio frequency choke, and a radio frequency choke, which is say 10 turns on an FT37-43, theoretically has 0 ohms. It's from a DC point of view, it's got nothing. So anyway, so what I'm trying to say is presented with just the transistor and you want to design this amplifier here, what would be the best approach? So there's a few things that we need to get. So we need to set, as we just mentioned before, our ICQ, our quiescent DC current. We need to know, and now there's different ways of writing this, our beta or capital HFE if you're using the H diagrams for our DC current gain. Now, we're just sort of talking about this for a little while here. Here goes the a spec sheet for a 2N3904. A couple of things we can note here. The maximum collector current we can take through this is 200 milliamps, which is great. We won't be exceeding that in any way, shape or form. And over the page, there's a couple of values here. We have HFE, DC current gain. Now the current gain here, they provide some different values. And the columns is min, max, min, typical, and max. So we look at the DC current gain here. Depending on what the collector current is for a nominal 1 volt VCE, we get typically different gains through it. So in terms of this value here, one approach would be to take the nominal 10 milliamps, and we would say, okay, minimum is 100, maximum is 300, so let's just work on a value of say 200 as a median between those two values there. But we also got another value here which I've used before, potentially incorrectly, and again why I'm bringing this up now to sort of open up the discussion is our transition frequency. So this is the frequency at which, so typically here they're saying here in the typical column, at 270 megahertz, the gain of this particular transistor is 0 dB. And if we, so that's where I've been using that sort of that calculation in previous amplifiers, that beta equals FT divided by our frequency of operation. So in this particular case, 270 divided by 3.5 megahertz would give us our beta for 3.5 megs. I don't think that's correct, and why I say that is because we're trying to work out what our DC biasing point is. In other words, our quiescent steady state, no input biasing conditions are for this transistor. And once that's all been set up and we've got our bias point set, hopefully getting our collector at halfway between VCC and VE, we can then apply an input and start to drive that output up and down in line with our input. I think it's an inverting amplifier. So I don't think, and like I say, I'm open to feedback, that it's correct for working out a DC quiescent biasing point to use that approach. I think the better approach is to, and I have done this before and I just haven't done it for the last couple of amps, is to use the HFE DC current gain, which then introduces another question here, because, or another, something to think about is that minimum value varies depending on how much collector current's going through it. So there needs to be a decision made where, what is our notional collector current going to be through this. In previous amplifiers I've chosen 1 milliamp, I've used 10 milliamps, in some cases I've gone right up to 42 odd milliamps in order to drive down a little RE. But again, you know, what is or what should be a typical value? Now one can argue, if we were to use these characteristic curves as for some guidance, here we have here IC in amps, or 10 milliamps, and for a 13.8 volt VCC, that certainly provides quite a nice, there's quite a large area there that we can drive that quiescent point up and down when we start to apply an input. So maybe a good approach for these sorts of amplifiers, and certainly for an amplifier based around the 3904, is to say, hey look, let's just use 10 milliamps. So maybe that's what I'm going to do sort of moving forward, is just use that value there. So 10 milliamps IC, I've got a minimum of 100, a maximum of 300, so I'm going to use 200. So maybe from this point onwards, for using these sort of calculations, and this is where I'm opening this up to sort of discussion, is maybe it should be let IC, Q, or our quiescent current, equal 10 milliamps, and we'll use a beta DC of equal to 200. So once we've established that as our sort of our principal constants, I guess, to use, we can then go forward and work out what the various values are. And I suggest that in some of the documentation around the place, okay, full stop, draw a line there. So let's look at RE. Oops. Let's look at RE. So RE is this resistor here, hanging off our emitter to earth. We've said that 10 milliamps is passing through it. We actually said that 10 milliamps is our collector current, and we can use that rule of thumb that IC is approximately equal to IE. So we can see here that another rule of thumb that's quite often used, and I mentioned it before, is you set the emitter voltage, so the voltage at the emitter, to be no less than 1 volt. And you can see the reason why here. As soon as you start to go below 1 volt, you start getting to this non-linear region of the transistor characteristic curves. So we always want to have at least 1 volt to get us into the linear portion. You'll note in the past I quite often use a rule of thumb of just 10% of VCC. And for VCC, for a typical ham radio, is either going to be 12 volts or 13.8. So straight away we've got 1.2 or 1.38 volts. So, you know, we are greater than or equal to 1 volt with that approach. I'm probably just going to stick with that sort of rule of thumb of just 10% of VCC, as opposed to, say, letting it equal 1 volt. So getting the old trusty calculator out there, so let's say we're 1.38, so using Ohm's law, therefore RE equals the voltage drop across it, 1.38, divided by 10 milliamps, should be 138 ohms if I recall. 1.38, enter, 0.01, divide, of course 138 ohms. And then we would look for the nearest standard value to be closest to that. While we're here, we can talk about that emitter bypass capacitor there. As we've said before, if we have this fully bypassed, our voltage gain will just be a function of RL, but the more and more unbypassed emitter resistor that's presented, therefore our voltage gain is the RL divided by that portion that's divided. But anyway, if we were to have a fully bypassed emitter resistor, then the rule of thumb is at the lowest frequency, the capacitive reactance of that there should be less than or equal to 1/10 of RE. So we said that RE is 138 ohms. We want it to be less than or equal to 13.8. And noting that XC equals 1 over 2 pi FC. So we can, for say the 80 meter band, so that would be our lowest operating frequency we just mentioned, would be 3.5 megahertz. So it'd be 2 times pi times 3.5 megahertz, or 3.5 times 10 to the power of 6 times C would equal to, and we'll just set that arbitrary to 13.8. So we can swap that around. C equals 1 over 2 pi 3.5 megahertz times, what do we say, 13.8. And then we can solve for C. Might be a bit easier to zoom out there. So that would be the approach for working out our emitter resistor and our emitter capacitor, or bypass capacitor. So next up is, and I'll just tear that bit of paper off there, would be the value of R2. So maybe I can just have it on the screen there, we'll have to see. R2, sorry, it's a little bit difficult here with the camera. R2, as I've said, noticed before, I might just repeat it here for the sake of for completeness. Again, from our rule of thumb is for this voltage divider biasing here to be nice and stiff, we want to have at least 10 times the base current flowing through here. So if we have 10 times the base current flowing through here, we'll have 10 times through R2, and then plus we'll have the addition of the base current flowing through there. So R2 will see 10 times, and R1 is going to see 10 plus 1 equals 11 times. And it's just straight out Ohm's law. So the voltage here across this R2 divided by 10 times our base current, we can work out what R2 will be. And this voltage, yeah, okay, let's just do that one first. So the voltage here, we said, using what I've been traditionally doing, a tenth of VCC would be 1.38 volts. So 1.38 plus 0.7, and then that would be the voltage there because that's at 0 divided by 11 times our base current. So just working that one out, we would say 1.38 plus 0.7 divided by IB, and we know that IB equals IC divided by beta. Beta is what we decided was going to be 200 from the specification sheet. So that would be IC is 10 milliamps divided by 200. So back into this formula over here, we would have 1.38 plus 0.7 divided by 10 times our base current, which will be, like I just said, 10 milliamps divided by 200, and that gives us, we'll just smash it out, 1.38 enter, 0.7 plus 10 enter, 10 a to the minus 3 enter, 200 divide times divide, 4160 ohms. And again, we would find the nearest standard value for that, so maybe 3.9k perhaps. So next one is R1. So that's our second resistor in that voltage divider there. And again, from Ohm's law, it's going to be resistance equals voltage divided by current. So resistance equals that voltage there minus that voltage divided by 11 times our base current. So 13.8 volts minus 1.38 plus 0.7, in other words our emitter voltage plus the voltage across that emitter to base, divided by 11 times 10 milliamps divided by 200. And I haven't pre-done these, so I'll just quickly smash that one out as well rather than trying to guess. 13.8 enter, 0.7 plus minus 11 enter, e to the minus 3 enter, 200 divide times divide. So 21.309 k ohms, so maybe a 22k perhaps. So I think we have now solved for our emitter resistor, we've solved for R1, we've solved for R2, and now we're just left with the value of RL. For say an audio amplifier, we would want to have our emitter voltage to be approximately, or close to, half of VCC. Now we need to acknowledge that there's going to be some voltage drop across our emitter there, or at our emitter. So in fact it would be VCC here minus a tenth VCC divided by 2 would be sitting out there. So once we work out that voltage, then again from Ohm's law, 13.8 minus that voltage that we've now worked out divided by 10 milliamps. and we can solve for our RC, our collector load there. A little bit different if it's a RF amplifier. So we have talked about RF amplifiers in the past, so different options there. We can do, and what I've done several times is have the transformer in the collector, and typically if you look at say the solid state design for the radio amateur, they talk about wanting to present to the collector 200 ohms. So typically we would have 50 ohms as a load. It could be anything, but 50 ohms is quite often a typical design load. So then we need to work out a transformer that would transform 200 ohms, or more the point, 50 ohms up to 200 ohms. So as we've seen in the past, 200 divided by 50 square root will give us n. And why that arrangement there? Because 50 times n squared equals 200, which is the typical formula for impedance transformation through a transformer. So therefore, making n the subject, 200 divided by 50, square root both sides, and you can work out your n. Of course, that gives us a value of n equals 2, and then quite a common transformer ratio for the frequencies I'm using would be 12 to 6. And just to repeat why that's quite a common one is because the other rule of thumb we want is to, now that we've established this transformer here, the smallest winding is the 6-turn winding, and we need to make sure that its inductive reactance, or XL, noting that XL equals 2 pi FL, is approximately equal to 5 times 50 ohms, or its inductive reactance is approximately 5 times the load that's hanging across it, in this particular case 50 ohms. So I won't do it here, but again you would plug in, you would find out L. So L would be for a FT 37-43. You would just find out using FT 37-43, 6 turns, what does that come out to be? And I can't quite remember. I think it's roughly 6 microhenries. I can't quite remember. But again, once you've found out what it equals, plug it back into here, 2 pi F. And because F is on the top line, it's going to be at our lowest frequency of operation, which will be, again, if we were say to pick on the 80 meter band, would be 3.5 megahertz. So plugging that in, because noting if it was say 40 meters or 20 meters or higher frequencies, anything if that's increasing, that's going to increase, and therefore that's going to get better and better and better. So that's why we choose the lowest frequency. And as we mentioned in that last video, is while that is a general rule of thumb to present 200 ohms, as Lars quite rightly pointed out, that's not necessarily what the collector impedance is. And that's when we talked about, and I don't particularly want to go into it again too much, the device, the transistor itself has some kind of collector resistance or impedance, and that's the voltage at the collector. So in an open circuit, there's no current flowing through that internal resistance, so I'll just call it RC internal for lack of a better term. If there's no current flowing across that, there's no voltage drop across that, therefore the voltage here must be the voltage there. So we'll just call that voltage R. If we were now to put across, all things being equal, a resistor, a variable resistor, and we keep measuring that voltage there, we now have current flowing through both these resistors. So both these resistors are now having a voltage drop across them. So if we keep varying this until this voltage is now the original voltage divided by 2, then we know that this value here, R, equals RCI. I know that's an incorrect term, but I'm just using it for the example. And so that's just fact. From a voltage divider, if that voltage is now V divided by 2, that equals that. And once you know that, you can then say, right, or having now established what this unknown internal resistance is, or impedance. Impedance, of course, is an R plus J term, so I'm only talking about the resistive portion. I'm not worrying about the reactive portion, be it capacitive or inductive. But anyway, suffice to say, once you know R here, you can then create that transformer to transform from 50 ohms, our desired load, to now match what this value here is. So whatever R turned out to be. And then again, using the same approach, 50 times n squared equals R, therefore R equals, let's say again, solve for n, and then work out what your transformer needs to be. So thanks to Lars for pointing that out and reminding me on that approach. Rightio, so I'm going to leave that there. I've been rambling on for several minutes now. So like I say, the whole idea of this video here was to more introduce and to solicit some feedback or some comments on the best approach for designing, in my particular case, what I like to design, the common emitter, voltage divider biasing, Class A amplifier, using, say, a 3904, when you've just got the specification sheet. So I've presented here an approach that I think is probably not too far off. I know if you delve through the textbooks, the formulas can get very, very complex with alphas and betas and deltas and all sorts of things to get things exact, but I'm trying to find a nice, easy, simple way of designing these using some pretty straightforward rules of thumb. You know, the 10th of a VCC, for example. 10 times the base current through here, etc., etc. So I'm trying to find a nice, easy, simple approach where you can get the values you need out of the spec sheet and then create a relatively effective amplifier. So I'm going to say 73s there. Please, any constructive feedback, more than welcome. And I'll wish you again 73s, and I will peel off here. For interest's sake, got a little bit of work to do on the weekend. Let me just undo that. So the amplifier, or the IF amplifiers are done. So let me just come down there a bit. So it's just a matter of now finishing off constructing this just to get the superhet going. Over the back here we'll have the bandpass filter coming in with the RF amplifier. I'll probably look at redoing an RF amplifier based on the discussion we just had tonight. But anyway, suffice to say, RF will be coming through here, through the mixer, through that bidirectional IF amplifier there. It's got its own 6-volt power supply, and I'll talk about that in another video. I was initially thinking about converting this to 13.8 volts, but that wouldn't have worked because the breakdown voltage would have been exceeded. These little devices here are only allowed to have 6 volts across in reverse, not 13.8, so that wouldn't have worked. Our 2 crystal filters there with the switching relay, depending on if it's on CW or single sideband, coming through the second IF amp into that second mixer, and then across to the AF amplifier over the back there. So that's a bit of a weekend task just to finish off wiring that up, and we'll go from there. Anyway, 73s, and we'll talk to you next time.